Here we go with some more related rates today. So this time we're going to have much more fun pictures to try to draw. So we've got Sue standing on a dock. So like I said, I'm one of the best picture persons in the world. Not. So here's Sue. She's pulling in a boat. She's pulling a boat into the dock by means of a rope tied to the string of the boat. So here's my boat. Here's this. She's pulling it in. If the ring is 2 foot above the water level, so this is 2 foot, and her hands are 7 foot above the water level, and she's pulling the rope in at a uniform rate of 2 foot per second, we're going to find the speed which the boat is approaching the dock when it's 12 foot from the dock. Wow, a lot of things taking place here. Well, the first thing I'm going to do is I'm going to take out part of my picture. So as I can see right here, I have a right triangle. I'm going to recreate that right triangle. And I now know that this side is 5. I'm going to use X, Y, and Z again, as I've done in prior problems. Well, what do I know? What am I given? I'm going to reread this. I am given that she is pulling in the rope at a uniform rate of 2 foot per second. Well, that's this right here. So that's side Z. So side Z is changing with respect to time at 2 foot per second. Now we have to keep in mind that that is actually going to be a negative 2 foot per second because the rope is getting smaller and smaller. It's getting pulled in. It's going to the left. The next thing I know is just really what y is equal to. And I've already marked that in the picture. So I'm going to find the speed at which the boat is approaching. So that would be the change in the x here. So I'm going to find dx over dt when the boat is 12 foot from the dock. So when x is equal to 12. The formula I need is Pythagorean theorem. X squared plus y squared equals z squared. Now I was given the y part, so I will go ahead and plug that in right now because it will make it easier when I go to take the derivative. So I have the derivative of x squared is 2x dx over dt. The derivative of 5 squared is just 0 because the derivative of a constant is 0. And I have 2z dz over dt. I'm supposed to find dx over dt. I'll plug in some known values right now. This is still 2. The x value is something that I still need to figure out. No, I don't. That's what they told me. It's 12 down here. It's 12. I'm supposed to find it when x is 12. I know this is a 5, 12, 13 right triangle, so I know that z is 13. I have 2 out here in front, and I'm going to find dx over dt. The last bit of piece of information I need is dz over dt, which is negative 2. Well, this number right here, 13 times 2 times negative 2, happens to be, 26 times 2, negative 52. And over here I have 24. Divide by 24 on both sides, I get dx over dt is equal to negative 52 over 24. That does reduce down to be negative 13 over 6. And my label would be feet per second. Alright, in this problem I have a hot air balloon that is being set off by a boy leaning against it. And so the hot air balloon starts rising and the boy starts running away. Bad picture again. And we're ready to start talking about it. The balloon is rising at a constant rate of 6 foot per second. And the boy is running away at 8 foot per second. So that means that I'm given, that is, if I'm calling this x, y, and z, I am given that dx over dt is equal to 8 foot per second, and dy over dt is 6 foot per second. This is a right triangle, so we're going to be having to use Pythagorean theorem. I did forget to write down what I'm trying to find. I'm trying to find out how fast the balloon and the boy's distance is changing. So that would be dz over dt. I'm supposed to do that when t is equal to 5. So taking the derivative of this, I have 2x dx over dt plus 2y dy over dt equals 2z dz over dt. And I'm going to divide everything by 2, so that gets rid of those 2's out in front, and I don't need to worry about those anymore. If I start plugging in the values I have, I know that this is 8. I know this is 6. And I know that after 5 seconds, y would be 30. Because it's moving at 6 feet per second, so every second it goes up 6, so after 5 it would be 30. After 5 seconds, this x would be equal to 40. The boy would be 40 feet away because he's running at a rate of 8 foot every second. So at 5 seconds, he'd be 40 feet away. In a right triangle, this would be a 30, 40, 50 right triangle. So I know z is 50. All right, let's finish plugging those numbers in then. I have y is 30. I have x is 40. And z is 50. dz over dt is what I'm trying to find. So I have 320 plus 180 equals 50 dz over dt. So I have 500 equals 50 dz over dt. Divide by 50 on both sides, and dz over dt is equal to 10 feet per second. Another related rate problem. Oil spilled from a tanker anchored in the harbor spreads out in a circular slick. So I have a circle. When the rate of the slick is 100 feet, okay, so when this is 100, the area of the slick is increasing at 50 feet squared per second. Find the rate of increase of the radius of the slick at that moment. So I'm given that the area is changing at 50 feet squared per second. I am supposed to find how fast the radius is changing when the radius is 100. And r equals 100. Alright, the formula I'm going to be using is area of a circle, so a equals pi r squared. Take the derivative with respect to time, dA over dt equals 2 pi r dr over dt. Well, when I plug in the known values, one of my known values is dA over dt is 50. I have 2 pi. I'm plugging in 100 for r. And I have to solve for dr over dt. I end up getting 50 equals 200 pi dr over dt. Divide by 200 pi on both sides. So that gives me 1/4, or 1 over 4 pi is my dr over dt. And radius is described as, in this problem, feet, and then the time is in seconds, so it's feet per second. Next example, I'm actually going to skip, but I will tell you that the answer is 100 feet per second. I'm going to continue on to this next problem. A body travels on the circle x squared plus y squared equals 25. When the body is at 3, negative 4, the x component of velocity is 2 units per second. So we're talking about velocity. We know that's the derivative. So dx over dt is equal to 2. Find the y component of the velocity. So we're supposed to find dy over dt at that point. Well, I need to just go ahead and take the derivative of this circle. So the derivative would be 2x dx over dt plus 2y dy over dt equals 0. I need to solve for dy over dt. So what things do I have? Well, I know that I have a 2. Right here's my x, and there's my y, so my x is 3. My dx over dt is 2, plus 2 times my y value is negative 4, and I have dy over dt equals 0. 2 times 3 times 2. Well, let's see here. That's 12 plus negative 8 dy over dt. I'm going to solve for dy over dt. Move the 12 over and then divide by 8, or negative 8, which gives me negative 12 over negative 8. That definitely can be reduced. 4 goes in each one of those, so I have the answer being 3/2 units per second. I have 2 final problems for this day of related rates. The first one talks about the radius of a circle increasing at 3 centimeters per minute. And we're going to find the rate of change of the area again. I'm not going to sit and draw a picture of this. This is telling me that dr over dt is 3. I'm supposed to find dA over dt. Hopefully we're getting a little bit quicker at these simpler problems. So we have A is equal to pi r squared. dA over dt is equal to 2 pi r dr over dt. I'm going to do this problem twice, so once for part A, once for part B. Part A, dA over dt would be equal to 2 pi. This time my r is 6, and my dr over dt is 3. So I end up getting 2 times 6 is 12, times 3 is 36 pi. Label for area is always square units, so in this case, square centimeters per minute. Part B, I'm going to use 24. So I'm going to have dA over dt is equal to 2 pi. Put 24 in for r this time. And dr over dt is still 3. I end up getting 2 times 24 is 48. 48 times 3 is 144 pi. My area is still squared centimeters per minute. So that's part B. Last problem for this particular day. We have a spherical balloon being inflated with gas at 800 cubic per minute. I left that off. That'd be cubic centimeters per minute. Well, I know cubic is talking about volume. So I know I'm going to be needing the volume formula for a sphere, which is 4 pi r cubed. 4 thirds pi r cubed. The derivative of the volume with respect to time would be 4 pi r squared dr over dt. I'm supposed to do this in 2 parts again. How fast is the radius of the balloon increasing at the instance the radius is 30? We're actually going to be solving for dr over dt. Remember the 800 was dv over dt. So before I actually start plugging in numbers, I am going to go ahead and solve dr over dt. I'm going to say this is 800 because that's going to be the same for parts A and B. And I will solve for dr over dt, dividing 4 pi r squared off both sides. So that gives me 200 over pi r squared is my dr over dt. Part A, we're going to find it for 30 centimeters. So dr over dt is equal to 200 over pi. We're plugging in 30 for our radius. So I end up getting 200 over 900 pi, which simplifies just to be 2 over 9 pi. The radius would be in centimeters, and then the time is minutes, so centimeters per minute. And part B, I'm going to just plug in the 60 instead of the 30. So 60 in for the R. That gives me 200 over 3,600 pi, which will reduce down to be 1 over 18 pi. So in part B, I get 1 over 18 pi centimeters per minute.